Perhaps I leave the door open a bit more, right? See how it goes. I don't know about you, but I'll fall asleep while standing here with this temperature.
It's even worse in the back now.
Yeah?
Yeah.
Oh, higher up there.
Yeah.
Is it hot in the back there? Yes. Here too. Yeah.
I think we should try and leave the doors open.
Yep. Okay. Keep going up. Where are we going? Okay, I started talking about the great promise of personalized medicine and doing, sequencing and finding out personal proteins perhaps and personal microRNAs and personal I don't know what to really understand the system, such that if you go to a GP, the guy won't even want to know your name anymore. That's old school. Give me your chip, your DNA and stuff. That's you, right? And then, so I've got a bit of a headache. That's fine then. Go in the machine. Okay, I see what's wrong. This pathway is a bit disturbed. Do this, do that. And it presses a button, and then pharma, because this pharma problem, the pharma crisis has been solved, and at your night cabinet at home, the pill will be there. No, it will just be given to you while not knowing, because you've got this chip that chemicals are being produced there, and then immediately, right? Something else. The codon table. How many letters produce a protein on DNA? Who knows that? How many letters? I think I've asked you this question before. It's 3 letters, right? You know why? 4 times 4 times 4. Should be more than 20, 20 or more. So codons are 3-letter positions. People have been experimenting with 4-position codons. That is 4 times 4 times 4 times 4. That's 64 times 4. That's a big number, right? 256 or something. Okay. More combination possibilities. Then you can encode amino acids that have not been seen yet. There are antibiotics that look very much like a little protein with a ring structure, but with some funny amino acids. Suppose we could build them ourselves. How's that? Build your own drugs. Dutch is in history. Where did people, sailors in the old days, in the 15th, 16th, 1700s, they died of what? Vitamin C deficit, right? Rats will not suffer that problem, because rats are still able to produce vitamin C themselves. That's clever, eh? We lost that in the course of evolution. So rats don't need to find oranges. That's why they don't eat them. There's no need. Right? So you see that, the genetic makeup is different in people across species. So if we could change the architecture of the system as we live, we can build new cells. All of it's scary and frightening, I know. But anyway, there are possibilities. We can do things at various levels in not too long. Anyway, and there have been some experiments that people were shocked by because it started working. 4 base pair coding. Anyway, let's talk about, in the light here a bit. I have to press the absolute right button, otherwise I'm in trouble for the next half hour or so. This is hey. I've got away with it. It's just very light here. Are you fine with this light level? Can you see it in the back as well? Okay, then I'll leave it. Okay, so this is the longest gene in humans. It's, what was it, 2.4, roughly 500,000 base pairs, a big gene. It has almost 80 exons, 79. So, exon, exon, and so on, 79 times. The disease is terrible. It's rarely girls because it's X-linked. This is what happens to boys. They get deformations and their muscles give up and they die pretty young. Terrible disease. 2 variants, one even worse than the other, but it has to do with just a mutation, point mutation. Something on this huge gene going wrong, leading to disease. Molecularly, we know exactly what's happening. So we should be able to solve it, and then problems start coming up. It doesn't work. This disease cannot be. There are different companies, to show you here. Some medication has been developed about exon skipping. It turns out that the mutations there have to do with what exons are being expressed in the protein and which one not, and so on. So this is a perfect candidate for gene therapy. There is just one lethal gene leading to this horrible disease. So if we could repair that gene or put it in the system an extra copy, that is functioning properly, those kind of things, gene therapy. So, and here's that new technique that I mentioned to you. So, look that up if you didn't look at it yet. CRISPR is really, basically you could say you can build a gene anywhere in the genome. In the old days it was, it could land roughly here, we're not quite sure. And that could be dangerous, but now they can pretty much determine exactly where the gene should go. And that is fantastic. So politicians will be okay because a few people died in, over the last decades in trying out and finding out about gene therapy. And then it's all very bad. And people are for religious reasons, we can't do this. It's all terrible. So then we can save a lot of people. Okay, that's one disease. An even simpler disease on the molecular scale is CF. Terrible. Cystic fibrosis, slijmziekte in Dutch. Some people have a higher chance. It's a faulty gene. You need two incorrect copies, so it's not X-linked. So later, boys and girls have it, a bit more girls even, but roughly the same proportions. A lot happens here. You sweat. You have the most severe problems are respiratory. Your lungs give up. They die. That's what's happening. You get 20 to 30 years old. The record is 36 years old. People die. The incidence in the UK and Ireland was a bit up, so it was called the Celtic disease before, but that seems not true. The Ashkenazi Jewish population has a higher incidence. The gene is more frequent there. But anyway, this is we don't know everything about it, but enough so that the gene product is called CFTR, the cystic fibrosis. What's in the name? Transmembrane conductance regulator. It is about a protein that's in the cell membrane. Now, putting stuff in and out of the cell, that's disturbed, and that's why a lot of tissues are affected, but most severely lung tissue. And it's about transporting chloride ions in between cells. That's disturbed in it, that's a big problem, and you get all kinds of gluey mass in your lungs. And that's why it's called, it's fibrosis, and then the cells give up and they die. That's what's happening, throughout your lifetime. Here's the molecular biology. What happens? There is a deletion of 3 base pairs, the red guys here. So it's a gene of at least, protein's already 500, it's a gene of at least 1500 base pairs, maybe 2000 base pairs or something, where just 3 letters fall out. Here is the protein encoding, and what happens? It's not in frame, as you can see. It's the C, the third position of this frame here, and then 2 positions of the next frame, but it works out because of the redundancy of the codon table, that just 1 amino acid drops out. So the protein is just lacks 1 amino acid. And that amino acid turns to be here, that's the phi that is encoded here. The protein functions pretty okay, basically. This is what happens, it's in the cell membrane here, and this is this chloride core, multi-domain protein. More about that in the course Structural Bioinformatics. You learn all there is to know about proteins there. And so this protein functions, but it's detected in the cell as, this is a bad guy. It's a great system. It's dumped, it's put in the wastebasket. But it shouldn't have been, because it's still functioning. But the system is triggered not optimally here. So that's what happens. So we should just be able to repair the gene, put this in. That's where the story stops. We don't know how to do this very well. I told you the stories about these weakened viruses, the inhalers, they tried that. Doesn't work. So now all hope is on CRISPR-Cas9. And so genetically, what's happening more here, but read it at home. It's here on the chromosome. It's 7, I think. Yeah, there you go. Chromosome 7. And but there is one other thing. This is the dominant cause for roughly 80% of the cases. But where is that thing? There are more than 50. I didn't put it in here. Maybe here. No, there are roughly 1,500 different mutations known to be associated with this disease type somewhere in this region. So the most dominant is this 3 base pair deletion, but there is other stuff leading to different severity of the disease. So if you develop a drug for the dominant cause, you've got 80%, but the 20% are still in trouble. So what do? And basically, if you know the cause, being able to repair it, to address it, is another matter. For example, even if the drug is perfect, it works, it's non-toxic, it's known to work in vivo, in vitro and in vivo even. How do you administer the drug? How does it get there? How do you get a protein in your intestine? It's being degraded in your stomach. What do you do? make something around it. Oh, you know, you get all kinds of clever stuff. Like here, people experimented, okay, the cellular immune system. You know what? We weaken the immune system. Oh, but now you get all kinds of other diseases. Now, proteins that are not caught, you know, bad guys. So, okay, you trigger it. So you're trying to work with this very balanced, complex system. And you get from one problem into the other, right? So that's, but hope is on CRISPR-Cas9. Okay, so we often talk about we talk about complex diseases, that's multi-gene diseases. And if it is a complex disease, it should be a simple disease. Not so simple, I can tell you. And certainly if you talk to patients, this is not a simple disease to have. Horrible. Anyway, we should do something about this, you agree? You are here to do something about it, build something. So here is one step on the way. Little jump into the data. We have many, many databases. And each little circle here is a database. The life science corner is here. So this is a world of linked open data where all these data resources, maybe here is physics, here is the weather, and here is sort of a mental database or a neural database, and all kinds of stuff. And so there are many, and at the moment, yes, databases are being connected, the technology is being built to do that, but all of this is still quite cumbersome. And having then an analytics tool that says, right, here is the body of knowledge, now I'm going to ask nice questions to the system. Maybe I'll formulate them in the English language. So then, that will be great, right? So we're not there yet. Is that a question?
What's that in the middle? Was it the database that's in the middle?
DBpedia. This picture has been made with the maker of, I'm blindly guessing, right? I think this picture was made by the guy in the middle. How's that? There's no other reason, I guess. So there's no reason why something should be more toward the middle than others. What you see is also maybe the number of connections in between. So if the most connected database, you make a picture like this, then it makes maybe sense to put the most connected one in the middle. Otherwise, you get too many lines, right? But you can't see the lines anymore anyway. The dark stuff in the back. But okay. So here are, what kind of databases there are. So here is in a little corner here. This is the unit. So I'll fill you in a little bit to give you a feel. What do you need to do in terms of technology to get this going? And there you see here that we have the knowledge of information is called a triple. And the system that is very often used is called Resource Description Framework, or RDF. You'll hear this more, certainly if you stay in the IT domain. RDF is becoming dominant. A lot of computer scientists in semantic web technology. Semantic is about meaning, right? The data works within this framework, RDF. And the unit of information there is called a triple. And a triple is a subject, the thing you talk about. I give a protein. And then there is an object, and then there is a relationship formulated by means of a predicate. So you have a subject, an object, and a predicate. Protein A binds to protein B, for example, or interacts with. Or John, pupil of James, right? So you can build, and the idea that computer scientists have that all knowledge can be formulated like this. If that is true, this of course is factual data, binary data, situations. What do we do with scalar data when there are numbers? So you need to do something about it, but this is what happens. So, and then what can happen if you have protein B and you happen to know or have measured that protein B also interacts with protein C, for example, you can see what happens. Then you get a whole network of connected triples of objects and predicates. So the object of one triple could of course be the predicate of another one, right? And you connect, you make a big universe of triples, and people have literally done this for billions and billions of triples now. The triple store here at VU in a local computer with 2 years ago 15 billion triples. And people reason over that. So that is what becomes able to be do. So then to be possible. So then we talk about data interoperability, all of this, and all of these networks. So what could we do? This is it's happening, but this is what we need to do more and more. So here we have a connected triple store. Maybe this is all there is to know about malaria. No, this is malaria. This is all to know about a bug, right? An insect. So a lot of knowledge has been measured, and literature and papers have been written, and all of this is amalgamated in this big triple store that connects open link data. All of these data stores that have information about these two subjects. And now somebody asks a question like, does malaria have something to do with a bug? Who knows the answer? Yes or no? Very good. Okay. And it comes out because it not only yes, it might be, no, it tells what it's just doing here, and it's a simple operation. You look what nodes in these two networks overlap, are the same, or have a connection here. So this could be a whole bunch of proteins, and then you can say, oh, then we can start finding out this protein in this bug is helping malaria, or the other way around, or whatever. You can follow up by targeted experimentation, right? And this is sometimes even solve the question, but very often you get clues as to how to ask further questions, and that's important in science, or even how to become operational, right? Actionable knowledge you generate, to act upon, right? You can now do. We can now find this out and see if we can take the next step. So that's very good. So we need an infrastructure that allows people, scientists, maybe you can program, but maybe we should build further such that citizens can start asking questions, well informed. And what is very important, and that's a weakness currently with triples, the provenance. I mentioned fake data, right? What is the problem? Somebody says something, and you take it as truth. And we know now by the internet and companies that have, the idea of making money spreading disinformation purposefully is a problem. So what is the only weapon against it? Why do you say what you say, right? And in the old days, I think I said this already, when you would say, I've read it, that was enough, not anymore. But what is your source of information? And our brain, as we sit here, and even you, your generation, following story, right? Somebody comes to you, tells you a story about a fact. You tend not to trust that person to the full. You've heard hanky-panky stories earlier by this person. So your true grade is okay, half true now, okay? Then the next guy comes in and tells you the story. You trust this person far more. So the truth of the fact is much more. And when a third person comes in and tells you, they say, oh, now it's consistent. 3 different sources told me the story, it's true in your mind. With the internet, it could be just one incorrect fact that has been retweeted and you name it, and it comes to you from 1,000 different corners. You think it's the same incorrect message, right? Our brain is wired incorrectly. So we need systems, and we need things to weapon us against it, against fake news, because we are victims of it. So the only thing is get knowledge, how to deal with it, and I think, frankly, education, it's not about memorize this fact and do this, and this is correct and that's incorrect. It should become far more early on about why do you say what you say? What's the problem? What's the fact? What did you read? How did you get to this point? Very, very important, right? And in science and data, that's the main thing. Why is there this overlap? How was that measured? Was it reproduced, the experiment? What happened? Who did it? What lab did it? Yeah? And then very often it happens when we start doing this type of stuff, and then you find out, oh, that data element there must be incorrect. The whole system tells me off. So you can connect to the author and say, how did you get to this fact? And very often you say, oh, yeah, that might be wrong, indeed. I was not too sure about it at the time. So provenance and reasoning at this level is really very important. Okay, so all of this leads to something that is now known, at least in this country, but becomes internationalized fact. Stands for fairness of data treatment, accuracy, of course, confidentiality. That's, again, doctors saying, oh, careful, and people doing projects and saying, look, the paper has not been published yet, so we want to have secrecy. We only should work, and we should have access to the data. Others may after the paper, and then you have to be transparent. That's, of course, a hard one in politics, and all of these people who are doing their things for financial gain. So, important. One story again. Quick one. Dirk van der Pol is for 20 years in the business as a data scientist avant la lettre. So he was in data, doing IT, became even rich, was a very happy man. Then he became ill. He contracted thymus cancer, small gland somewhere here. And he had never heard about it in his family, they didn't know. So they extracted the thymus. He was ill, but he could live on. But then a few years later, 3 years or so, he developed a bad form of COPD, lung condition. Breathing is difficult. That was known as a genetical disease. It runs in families, and the whole family said, "You never heard about it. You don't even know the term COPD." So he went to his GP and asked the question, "Hey, is there a connection between my thymus being extracted and the fact that I contracted COPD?" And the GP went on Medline and checked, and he didn't find a paper where this was described. And then he should have said, "Look, I couldn't find any link," but he says, "No, there is no connection. The because I didn't find it. And if I didn't find it, it doesn't exist. Okay, anyway, so he took that message for a while, but then he started working on it and found out, ooh, maybe there is something. In the meantime, there was a couple of years later, there was a chat forum in the US, and he went on to that, and in little time he had a specialist in the chat, and he told him something interesting. He said, I checked Medline, I didn't find any connection, you knew that, but then there was a but I get this question a lot. Aha, he thought, I am too ill to work anyway. I love saying, you know what, I'll devote my life, whatever is left of it, into finding out what is the connection between the thymus and thymus extraction and COPD. I want to know. I'm a scientist, or I'm a citizen, but I'm a well-informed citizen. I'm a data scientist. I'm going to find out. Same story as my earlier story. Hospitals blocked him. He was considered a terrible troublemaker. Awful guy who wants to ask questions and find out stuff. Horrible. Why would you want that? So, but he persisted. And so he is now, and that's great, the actual world leader on the connection between thymus and gland COPD. So, that's great, but it cost him 5 years of trouble, writing angry letters, threatening with lawyers to hospitals, and then going, okay, here is your data, promise not to use it, to expose it to anybody. Got CDs that couldn't be read, that made his life as hard as possible. And so on. So, but he managed. So, how would it work, you think, if we had an infrastructure? So our pitch to the government is, give us a bit of money, we want to build this infrastructure, so that guys like Van der Pol can do this in 10 minutes. Ask the question to the system, link to open data. Why does it need, if there is, information is measured, papers have been written, why does it need to take 5 years to combine something and have a hypothesis? So this must be much faster. Your generation, right? This is the chance. Okay, so all of this also is called data stewardship. Because I don't know how you put your data, what do you do with your data in the course, what is the format you store it in? Is it Excel? Is it something else? Do you think that the future generation will take your computer and say, I know exactly what this data set is. It's well described. You put in why, what numbers mean. Is that what you do? What about your grandchildren? Will they be able to use your data? Be fair. Be honest. Fair is a term that I'll use in another. So the answer probably is no. So we should get there. Fair at source. Data should be, at least in universities, is produced with public money. And we hide it. We do everything to say, look, nobody should be able to use this. That's a crime, you might say. So we get now the movement, open science. Data should be deposited in a way that allows other people to use your data. There's no data to use other people. And maybe even in another way. Yeah? Small story, it's not on the slide I will tell about this. There is a Dutch church historian, and he has made a database of churches. All kinds of churches in all kinds of villages. But the data is well annotated with metadata, right? The time the church was built, everything, and also the day the picture was taken is also there. And now in one of these villages a murder happened, and they know that's the guy who did it, the baddie, the culprit. They can't find the handles, the fingers around it. And then at once the historian says, look, I looked in my database in that village, I see the picture of the church, and what's more, there is a gentleman in front of it smiling nicely into the camera. That's your guy. And he told you have never been there in the village. Now there's something to explain, isn't it? So, anyway. Meaning, a church database is used for forensic purposes. Very different. That is what we should do. The data is measured with an intent, but it might well be that it can be used for something else. These weather guys, they don't measure temperature and how much rain falls to help, depressed people. Well, come on, there's something else to do. But still, can be used as such, right? So that's really important. So that's why we need fair data, and I explain fair in a moment. That's a way to put the data such that it becomes reusable, maybe for another purpose. And there we go. Fair, the story starts in 2014 in the Netherlands, in a meeting with some people, I was there too, in Leiden. And then the fair stands for data should be findable, data should be... in fact was a good sort of, but anyway. In the leave it at this, I guess. I'll open it again. Interoperable, and data so you should be able to pool, to integrate data, and by doing that, data becomes reusable. Okay? And now it has been flying. Everybody talks about fair data. The G20 adopted it. The G7 adopted it. Europe, the EU has adopted it. European Science Cloud is now a big open, the EOSC, the Open European Science Cloud, 2 billion project or more, they don't know yet. Lots of money. They say all data should be fair, should be stored at source in a fair way. And I'll fill you in on what fair is a bit more. And what is very important, the funders who give us the money to do research now say, you have to come up with a data management plan. If you're producing data in your research, who is not producing data in their research these days, you need to have a data management plan. Your data should be fair, usable by other people. Okay, so, very important. What is fair data then? So, existing communities, so they could all use their data. That's as long as data is published in a fair manner. So it should be findable with persistent identifiers. Your data set has a name or something, an identifier that is findable upon the internet, and if you follow up on the link, the data is there. Even if the physical place is changing, that link still works. And that should be there for a defined period of time, say 20 years. Persistent identifier, and unique of course. You don't want to go to that data resource and not to something else when you follow up the link. Another thing is it should be accessible. But it doesn't mean it's always open. It could still be that there is a medical database where everybody agrees, this should be kept confidential or secret. But then still, the description of the data, what data set it is findable. This is about Parkinson patients, and this hospital has stuff, and there are maybe even 200 patients in, and then you go and say, can I access the data set? No. Okay. But there is an access committee. You could phone people and ask for permission to access it. So, it doesn't mean it's all open, but it should be accessible and described according to well-defined conditions. Accessibility, the A of fair. And then maybe a very important one is interoperable. And a way to make data poolable is you have a rigid description what the data set is. What is there? What do the numbers mean? What columns? What rows, for example? What does it mean? If you want to pool data, you need to do this. And that is, of course, the requirement when you put down a data set. If it's fair, you need to think about your metadata. And you need a data management plan to have all of this. It should be persistent. So all of these things you need to have in place. And I can tell you, this doesn't happen automatically everywhere. And if you have these things in place, you get the next step, the reusability. Yeah? We have reproducibility. That is doing the same thing again. But reusability has the thing on board, not only doing it for the same purpose, but maybe using it for another purpose. That's the difference between reproducibility and reusability. Okay? Now, there has been a paper in 2014, nicely cited, where it was a bit more defined. So here you see some criteria for findability, for accessibility, interoperability, and reusability, what you need, and then you see the word metadata coming up a lot, right? At least the metadata, for example, imaging data, is difficult to make fair, to be able to mine it completely, pixels, what does it mean, how do you treat it, there's different softwares for different data sets in the medical domain. One lung image is treated with a different program than another lung image, so it's a big jungle out there, but metadata should be fair. Okay, so this is what it means. If you have the data in an Excel sheet, you need to convert the data into fair format, and that has to do with metadata, as I said, but also the licensing, how to get access to this data set should be well defined, and all of this should be findable, right? So this is what you do. Now, this is in fact, the idea. It's like an hourglass. The idea is, it's not about, saying to people, you should use this standard, you're not allowed to use Excel anymore. Don't say that to a medical doctor, not Excel anymore. The guy jumps out of the window immediately. You use this and it's difficult, but it's great, you should do this. That doesn't, make many believers, right? So we need to do something else. And basically it's like comparing it to the internet. So it's an hourglass. We should really think about, what does everyone need here, and we find that well. The internet, you don't even think about it anymore. You just Google something up. And that is information that is spread over the whole world. It's distributed data. Why does that work? And that's the same thing. There are some well-defined web protocols that really everyone in the world adheres to, right? And the most important thing, technical thing, is TCP/IP. The way that addressing of the internet is being arranged. It's a small standard, but this was sort of agreed upon by the world, and everybody follows it. So that's what we need to do. And with the internet, we don't even think about this anymore. It's just normal. But you know, the world has to come together on a few, not on everything, on a few things. Yeah? And that is here we peddle that as the FAIR protocol. So it's not thick. People can have their own technological choices, build on it, but on a few things we should agree. And that are the FAIR principles. Okay, so basically it's data stewardship then, you know, if you're a data manager, a database is just not an Excel sheet anymore that is done somewhere. No, you need to do a bit more. You need to plan and have management and the long-term preservation. Data should not evaporate anymore, like I showed you this picture out of this Nature article, right? It should be persistent. Okay, so what's happening? If you talk about data, a lot of people talk about data these days, you see that, you know, people who produce data may talk differently than people who use data, right? And there's a big gap there. And, you know, this guy might say stewardship, sustainability, privacy, security, licensing, storage, and the guy at the other end. So in the middle there are all kinds of formats, how to store it, Sparkle queries, has to do with RDF, a querying system, metadata here, all kinds of standards, diconformatics, semantics, all kinds of standards, database management system, RDF is here, an API, who knows what an API is? You know by now, that's an application programmer's interface, something allowing programmers to access, not normal people, programmers, they use that to access data, and so on. And then, you know, the innocent user of all of this has, you know, how can I find the stuff? Well, ooh, what format do I need to take? Mind you, these days even, I shouldn't say this because you still have to do your internship, right? But anyway, 70% of the work that you will be doing is in beating the data into oblivion, you know, or to listening to you, you know, to do reformatting, get the data in a form that you can actually use it. That's still far most of the work. So to start asking, be able to start asking your question takes a lot of preparation. And we're talking here about bringing that time down, right? And that's still a challenge. So anyway, this is about you know, the user talking about the data. So what is the idea of interoperability? It's a simple mind's idea, but I've flashed it past you anyway. So here is about somebody wants to find a link between Alzheimer's and Huntington's. So you need to combine these two data sets. What is there to know about Alzheimer's? What's there to know about Huntington's disease? So and then two scientists from maybe different locations say, yeah, I think I have some data on Alzheimer's and I have some data on. So here it is. The one has this language and the other has that language. Fantastic. Now we are interoperable, right? We talk. And this is, you know, of course this is in language, but the idea is pretty much the same. You know, here's the data. Good luck answering your question. So bloody hell. So what is fair? You connect it and put both of these languages or formats, or you know, because you have these few standards, the data can talk together, and that's really, really very important. Okay, so what's not needed for this? We have a baseline of this data as it's measured. You see a lot of imaging data. It can be in all kinds of formats. You know, here you see this one. Remember that? So, you know, all kinds of formats, right or wrong formats, doesn't matter. Provenance, of course, very important. You know, how is stuff measured? What are the conditions? What is the pH? Blah, 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 blah. You need to have all of that. And then you get the fair transformation layer. And this is a technological choice. And a lot of systems now start using RDF, that I just mentioned, with the triples, as a resource to do it, to build these knowledge graphs using RDF. And if you have this layer, then all of these data can be in different stores, in different formats. It doesn't matter, as long as they're fair. They're elevated at this level, the data sets can talk, very important, so that's the level we're talking about. And if we have done that, then we can have, you know, a transformative world, disruption, have the apps on your phone. I want to know about this connection, click. Oh, interesting. I'll call my GP, tell him that he isn't all wrong, right? That's why you're so much loved by your GP if you come with these ideas. And so, you know, so this is the hope, and this is growing, but we need tremendous lot of stuff happening to make this really into a reality. Okay, so And we talk about fair data, and then we talk about data stations that publish fair data. We call those fair ports, right? Airports, airports. See the fun? We thought it was a lot of fun to do this. Anyway, so different fair ports connected, like hubs and airlines and airports. So there you go. So people are doing this and this. Then this. So we talk about distributed. We talk about big data. That's not so much a problem of big data. You buy a bigger disk, so more data. It's the fact that data are distributed in different places with different formats. And we have to pull it together. We're all about a rare disease, for example. There are 3 patients in Amsterdam, 10 in New York, 15 in Mumbai, 20 in Beijing. We need to solve it. We need a statistical base. We need to pull these genomes. How do we do that? That's the nightmare. And that's the real challenge. And FAIR helps there. So, a few things to end off with. So this is a network Elixir. This is a European project about data for life sciences. Very important. Look it up on the internet if you want. We are working in the Netherlands. It's called something like Elixir NL. With a couple of people. These are the leaders of these initiatives. So we do a few things here. For example, one of the things we make is a so-called digital research environment, allowing teams to work with their tools and data in a confidential way. So you can easily define, I work with these 40 people, but others can't see what we do. For now, you can open it up by pressing a button. But if you do the research, you don't want everybody to look into it. So safe and secure collaboration, secure as well. And we work with sort of an app store type idea of having your tools loaded in, so it should all be very, very flexible, that people can really use it. Another thing is I hope I have time to watch a little movie. To show you a little movie, I should say, about Eurocat and the personal health strain. I'll show you a movie, don't need to tell you about that then. This is about distributed learning. So the data is not pumped through the internet. A program is going to visit each of the databases, learns from it, does it a couple of times, and I'll show you the movie to fill you in a bit more. So the promise of FAIR is verification, make data sets fair at source. It turns out if you need to make your metadata. You think when you put the data in, I'll remember that. I know the data set. I have it in my mind, I typed it in or I measured it. Wait 2 months and say, now make your metadata. When was it? Ooh, don't know anymore. What was it exactly? What was this column? Oh, don't know anymore. So it's very difficult to make data sets fair afterwards. Really important to do it at source. And basically we're now saying the sequencers, they should write the data in a fair way right from the start. People shouldn't do this on all the programs. It should be fair at source. And then there's all kinds of libraries to verify, as we call it, the data. Basically, one more step is not only the data, it's the tools operating on the data, the analytics, what questions do you ask, various tools, and of course this should all compute, it's high performance computing on all kinds of clouds, and it should all be fair compliant, and this should really intimately work together. That it starts scaling the tools, the data, and the computation, the cloud set. That's very important, yeah? So, and all of this is to get to overhead-free, trouble-free science, ask questions, do not lose time with, preparing your data in complex research, okay? I'll gloss over this, you can read it at home. This is just filling in all of these projects, what we do. This is, you can go online and you see this. Elixir is organized in these platforms, compute data, there you go, tools. Importantly, interoperability is one of the main points. How to make data talk to one another, and of course training is the heart of it all. DTL is the Dutch Tech Center for Life Sciences, a Dutch organization. Interoperability, tying everything together. And this is good for you to know. BioSB, the Dutch Research School. Also master students can go to the annual conference, a lot of fun. We do a lot of things. We do a pub quiz and so on, and we have a good dinner, and we have fun, and there is the underworld, literally, where you can drink yourself silly until 5 o'clock in the morning. Next day, 9 o'clock lecture starts, but anyway. So, a lot of stuff happens, so check that out, BioSB, there for you to entertain. And here are my conclusions. Big data is here to stay. Like it or not, you'll have to work with it. We're in the data era. Data stewardship, therefore, is crucial. How to put down, how to deposit your data in a fair manner. Long-term data preservation, the fair data principles I alluded to. and a fair data backbone. Here, this is an official number by Europe. In the next few years, 500,000 data stewards should be educated. Bioinformaticians, who are these guys? Where are the universities to do this? 500,000. It's huge. So we need a lot we need to build up on it. Yeah? But it's a very important area. All of the big companies are data companies, as you know. And of course also 30% of our budget for this state goes into healthcare. It's huge societal cost of healthcare. So personalized precision medicine is the thing to go. Okay, that leads me to show the movie. If somebody has a reason, it's 2 minutes and 50 seconds under 3 if I get it running. Is there... Quickly. I go to here, press here. Hopefully it works. Do you see something? Does something work? You don't hear sound, right? Let's do this. Oh, sorry, the wrong one. Oh, be careful. I go back. Try again. Yeah, that would be good to do. Can you turn it up? I'm loud. Yeah, it's all the way up. I heard something, no? Where is it? I do this. Yeah. Things should off, then it works. Okay, go back.
The personal health training's main goal is connecting health data to make them more usable. Personal health management requires increasing amounts of personal data. But today, this information cannot easily be used because the data are produced and managed by various healthcare providers, authorities, and more by citizens themselves. These stakeholders collect and manage their data in different ways, making the data hard to find and use. Furthermore, personal medical information is very privacy sensitive. As a consequence, personal health data cannot be used easily by citizens themselves, by physicians, and by researchers. The personal health train goes to the root of this problem by building fair data stations. Fair protocols ensure that data are findable, accessible, interoperable, and reusable. These data stations are connected by tracks, which are strictly secured and protected. Fair data trains are constantly monitored, and only trains with the appropriate validation may enter a particular station. To secure privacy, every data station has rules. Each data owner has access to his or her secured station, and can easily request and control one's personal information. In addition, the owner can set rules for who can access the data and how it may be used. Communities with common interests, like patient societies, can choose to connect and organize their information through umbrella stations. With this access, a researcher can learn, for example, which cancer patients benefit most from novel therapies such as proton therapy. Or a citizen with a specific variant in his genome can be automatically alerted when new research results, insights, or possible risks become available. In this approach, the information is accessible for research, prevention, and education without the data ever leaving the station. With the personal health train, health data becomes available whilst individuals and institutions maintain control.
Okay, that's it. Any questions? No? All right. Lots of luck for what you're doing.
Nee, sorry, ik ben met op, maar
Anton. Ja, beter. Wakey, wakey.
Ik denk nog wat logistiek doen hier.
Alex.
Can't take it.